Light. Describe the dual nature of light. State what Albert Michelson's experimental value for the speed of light was. State the waves in the electromagnetic spectrum. Describe why certain materials are transparent to light. Describe opaque materials. Describe why shadows form. Describe the evidence that suggests light waves are transverse. Describe 3D vision. The big idea. Energy can change from one form to another without a net loss or gain. The only thing we can really see is light. But what is light? During the day, the primary source of light is the sun, and the secondary source is the brightness of the sky. Other common sources are flames, white hot filaments in lamps, and glowing gases in glass tubes. Almost everything we see, such as this page, is made visible by the light it reflects from such sources. Some materials, such as air, water, or window glass, allow light to pass through. Other materials, such as thin paper or frosted glass, allow the passage of light in diffuse directions so that we can't see objects through them. Most materials do not allow the passage of any light except through a very thin layer. Why do things such as water and glass allow light to pass through, while other things such as wood and steel block it? To answer these questions, you must know something about light itself. Is black light really light? Using a marker, write a message on a piece of colored paper. On the separate piece of colored paper, write a message with an invisible ink pen. Turn off the lights and exchange papers with your neighbor. Try to read the message on the paper using only a flashlight. Now try to read the messages using a black light. Observing. Which message was visible under the flashlight? Which message was visible under the black light? Predicting. Do you think you could see either image in the dark without the black light? How would you define light? 27.1. Early concepts of light. Light has been studied for thousands of years. Some of the ancient Greek philosophers thought that light consisted of tiny particles which could enter the eye to create the sensation of vision. Others, including Socrates and Plato, thought that vision resulted from streamers or filaments emitted by the eye making contact with an object, as shown in figure 27.1. This view was supported by Euclid, who explained why we do not see a needle on the floor until our eyes fall upon it. Up until the time of Newton and beyond, most philosophers and scientists thought that light consisted of particles. However, one Greek, Empedocles, taught that light traveled in waves. Figure 27.1. Some ancient philosophers believed that light traveled from our eyes to the object we look at rather than from the object to our eyes. One of Newton's contemporaries, the Dutch scientist Christian Huygens, also argued that light was a wave. The particle theory was supported by the fact that light seemed to move in straight lines instead of spreading out as waves do. Huygens provided evidence that under some circumstances, light does spread out. This is known as diffraction, which you will learn about in chapter 31. Other scientists later found more evidence to support the wave theory. The wave theory became the accepted theory of the 19th century. Then, in 1905, Einstein published a theory explaining the photoelectric effect. According to this theory, light consists of particles called photons. Photons are massless bundles of concentrated electromagnetic energy. Scientists now agree that light has a dual nature, part particle and part wave. This chapter discusses only the wave nature of light and leaves the particle nature of light to chapter 38. Concept check. What is the nature of light? 27.2. The speed of light. It was not known whether light travels instantaneously or with finite speed until the late 1600s. Galileo had tried to measure the time a light beam takes to travel to a distant mirror and back, but the time was so short he couldn't begin to measure it. Others tried the experiment at longer distances with lanterns. They flashed on and off between distant mountaintops. All they succeeded in doing was measuring their own reaction times. Olaus Romer. The first demonstration that light travels at a finite speed was supplied by the Danish astronomer Olaus Romer about 1675. Romer made very careful measurements of the periods of Jupiter's moons. The innermost moon, Io, is visible through a small telescope and was measured to revolve around Jupiter in 42.5 hours. Io disappears periodically into Jupiter's shadow, so this period could be measured with great accuracy. Romer was puzzled to find an irregularity in the measurement of Io's observed period. He found that while Earth was moving away from Jupiter, say from position B to C in figure 27.2, the measured periods of Io were all somewhat longer than average. When Earth was moving toward Jupiter, say from positions E to F, the measured periods were shorter than average. Light coming from Jupiter's moon Io takes a longer time to reach Earth at position D than at position A. The extra distance that the light travels divided by the extra time it takes gives the speed of light. Romer estimated that the cumulative discrepancy between positions A and D amounted to 22 minutes. That is, when Earth was at position D, Io would pass into Jupiter's shadow 22 minutes late compared with observations at positions A. Christian Huygens. Christian Huygens correctly interpreted this discrepancy. When Earth was farther away from Jupiter, it was the light that was late, not the moon. Io passed into Jupiter's shadow at the predicted time, but the light carrying the message did not reach Romer until it had traveled the extra distance across the diameter of Earth's orbit. There is some doubt as to whether Huygens knew the value of this distance. In any event, this distance is now known to be 300 million kilometers. Using the correct travel time of 1,000 seconds for light to move across Earth's orbit makes the calculation of the speed of light quite simple. Speed of light equals distance over time, extra distance traveled, divided by extra time measured. 300 million kilometers divided by 1,000 seconds equals 300,000 kilometers per second. The speed of light is 300,000 kilometers per second. Notes: light travels 1,000,000 times faster than sound. Do the math. How far in kilometers would a beam of uninterrupted light travel in 1 year? The speed of light is a constant, so its instantaneous speed and average speed are the same, c. From the equation for speed, v equals d over t, or in c equals d over t, we can say d equals ct, which equals 300,000 kilometers per second times 1 year. Introducing conversion factors for the time units, we find d equals 300,000 kilometers per second, that's the velocity, times 1 year, that's the time, and then I multiply it by the conversion factors to change 1 year to seconds so that the seconds will cancel. So first I multiply it by 365 days a year, then the years will cancel, and then 24 hours over 1 day, the days will cancel, and then 3,600 seconds per hour, and the hours will cancel. and that's left with d equals 9.5 times 10 to the 12th kilometers. This distance, 9.5 times 10 to the 12th kilometers, is 1 light year. Albert Michelson. The most famous experiment measuring the speed of light was performed by the American physicist Albert Michelson in 1880. Figure 27.3 shows how light from an intense source was directed by a lens to an octagonal mirror initially at rest. The mirror was adjusted so that a beam of light was reflected to the stationary mirror located on a mountain 35 kilometers away, and then reflected back to the octagonal mirror and into the eye of the observer. The distance the light had to travel to the distant mountain was known, so Michelson had to find only the time it took to make the round trip. When the mirror was spun, short bursts of light reached the mountain mirror and were reflected back to the spinning octagonal mirror. Figure 27.3, Michelson used a mirror arrangement to measure the speed of light. A. Light is reflected back to the eyepiece when the mirror is at rest. B and C. Reflected light fails to enter the eyepiece when the mirror spins. B. Too slowly, or C. Too fast. D. When the mirror rotates at the correct speed, light reaches the eyepiece. If the rotating mirror made exactly 1/8 rotation in the time the light made the trip to the distant mountain and back, the mirror was in a position to reflect light to the observer. If the mirror was rotated too slowly or too quickly, it would not be in a position to reflect light. When the light entered the eyepiece, Michelson knew that the time for the light to make the round trip and the time for the octagonal mirror to make 1/8 of rotation was the same. He divided the 70 kilometers round trip distance by this time. Michelson's experimental value for the speed of light was 299,920 kilometers per second, which is usually rounded to 300,000 kilometers per second. Michelson received the 1907 Nobel Prize in Physics for this experiment. He was the first American scientist to receive this prize. We now know that the speed of light in a vacuum is a universal constant. Light is so fast that if a beam of light could travel around Earth, it would make 7.5 trips in 1 second. Light takes 8 minutes to travel from the Sun to Earth and 4 hours from the nearest star, Alpha Centauri. The distance light travels in 1 year is called a light year. Concept check. What was Michelson's experimental value for the speed of light? Think. Light entered the eyepiece when Michelson's octagonal mirror made exactly 1/8 of a rotation during the time light traveled to the distant mountain and back. Would light enter the eyepiece if the mirror turned 1/4 of rotation in this time? Yes, light would enter the eyepiece whenever 1/8 rotation, 1/4, 1/2, 1, etc. In the time the octagonal mirror turned in multiples of light made its round trip. What is required is that any of the 8 faces be in place when the reflected flash returns from the mountain. Michelson did not spin the mirror fast enough, however, for these other possibilities to occur. 27.3 Electromagnetic radiation. Light is energy that is emitted by accelerating electric charges, often electrons in atoms. This energy travels in a wave that is partly electric and partly magnetic. Such a wave is an electromagnetic wave. Light is a small portion of the broad family of electromagnetic waves that includes such familiar forms as radio waves, microwaves, and X-rays. The range of electromagnetic waves the electromagnetic spectrum is shown in figure 27.4. The electromagnetic spectrum consists of radio waves, microwaves, infrared waves, ultraviolet rays, X-rays, and gamma rays. Figure 27.4, the electromagnetic spectrum is a continuous range of waves extending from radio waves to gamma rays. The lowest frequency of light we can see with our eyes appears red. The highest visible frequencies are nearly twice the frequency of red and appear violet. Electromagnetic waves of frequencies lower than red of visible light are called infrared. Heat lamps give off infrared waves. Electromagnetic waves of frequencies higher than those of violet are ultraviolet. These higher frequency waves are responsible for sunburns. Concept check. What are the waves of the electromagnetic spectrum? 27.4, light and transparent materials. Light is energy carried in electromagnetic waves that is generated by vibrating electric charges. When light strikes matter, electrons in the matter are forced into vibration. In effect, vibrations in an emitter are transferred to vibrations in a receiver. This is similar to the way sound is received by a receiver, as shown in figure 27.5. Exactly how a receiving material responds when light is incident upon it depends on the frequency of the light and the natural frequency of the electrons in the material. Visible light vibrates at a very high rate, more than 100 trillion times per second, or 1014 hertz. If a charged object is to respond to these ultra-fast vibrations, it must have very little inertia. Figure 27.5. Just as a sound wave can force a sound receiver into vibration, a light wave can force charged particles in materials into vibration. Electrons have a small enough mass to vibrate this fast. Light passes through materials whose atoms absorb the energy and immediately re-emit it as light. Materials that transmit light are transparent. Glass and water are transparent. Visualize the electrons in an atom as connected by imaginary springs as shown in figure 27.6. When light hits the electrons, they vibrate. Materials that are springy, elastic, respond more to vibrations at some frequencies than others do. Bells ring at a particular frequency. Tuning forks vibrate at a particular frequency, and so do electrons in matter. Figure 27.6. The electrons of atoms in glass can be imagined to be bound to the atomic nucleus as if connected by springs. The natural vibration frequencies of an electron depend on how strongly it is attached to a nearby nucleus. Different materials have different electric spring strengths. Electrons in glass have a natural vibrational frequency in the ultraviolet range. When ultraviolet light shines on glass, resonance occurs as the wave builds and maintains a large vibration between the electron and the atomic nucleus, just as a large vibration is built when pushing someone at the resonant frequency on a swing. The energy received by the atom can be either passed on to neighboring atoms by collisions or re-emitted as light. If ultraviolet light interacts with an atom that has the same natural frequency, the vibrational amplitude of its electrons becomes unusually large. The atom typically holds on to this energy for about 1 million vibrations, or 100 millionths of a second. During this time, the atom makes many collisions with other atoms and gives up its energy in the form of heat. That's why glass is not transparent to ultraviolet. but when the electromagnetic wave has a lower frequency than ultraviolet, as visible light does, the electrons are forced into vibrations with smaller amplitudes. The atom holds the energy for less time, with less chance of collisions with neighboring atoms, and less energy is transferred as heat. The glass of the vibrating electrons is re-emitted as transmitted light. Glass is transparent to all the frequencies of visible light. The frequency of the re-emitted light passed from atom to atom is identical to that of the light that produced the vibration to begin with. The main difference is a slight time delay between absorption and re-emission. This time delay results in a lower average speed of light through a transparent material. See figure 27.7. Light travels at different average speeds through different materials. In a vacuum, the speed of light is a constant 300,000 kilometers per second. We call this speed of light c. Light travels at a speed a very small amount less than c in the atmosphere, but its speed there is usually rounded off to c. In water, light travels at 75% of its speed in a vacuum, or 0.75 c. In glass, light travels about 0.67 c, depending on the type of glass. In a diamond, light travels only 0.4 c, less than half its speed in a vacuum. Figure 27.7. A light wave incident upon a pane of glass sets up vibrations in the atoms. Because of the time delay between absorptions and re-emissions, the average speed of light in glass is less than c. When light emerges from these materials into air, it travels at its original speed c. Infrared waves, which have frequencies lower than visible light, vibrate not only as electrons, but also the entire structure of glass. This vibration of the structure increases the internal energy of the glass and makes it warmer. As figure 27.8 shows, glass is transparent to visible light, but not to ultraviolet and infrared light. Notes: atoms are like optical tuning forks that resonate at certain frequencies. Concept check. What kind of material does light pass through? Figure 27.8. Glass blocks both infrared and ultraviolet, but is transparent to all frequencies of visible light. 27.5. Opaque materials. Materials that absorb light without re-emission and thus allow no light through them are opaque. Wood, stone, and people are opaque. In opaque materials, any coordinated vibrations given by light to atoms and molecules are turned into random kinetic energy, that is, into internal energy. The materials become slightly warmer. Metals are also opaque. Interestingly enough, in metals, the outer electrons of atoms are not bound to any particular atom. They are free to wander with very little restraint throughout the material. Think, why is glass transparent to visible light but opaque to ultraviolet and infrared? The natural frequencies of vibrations for electrons in glass matches the frequency of ultraviolet light. So resonance in the glass occurs when ultraviolet waves shine on it. These energetic vibrations of electrons generate heat instead of wave re-emission. So the glass is opaque to ultraviolet. In the range of visible light, the forced vibrations of electrons in the glass are more subtle, and re-emission of light rather than the generation of heat occurs. So the glass is transparent. Lower frequency infrared causes entire atomic structures, not just electrons, to resonate. So heat is generated, and the glass is opaque to infrared. That's why Metal conducts electricity and heat so well. When light shines on metal and sets these free electrons into vibration, their energy does not spring from atom to atom in the material, but is as visible light. This re-emitted light is seen as a reflection. That's why metals are shiny. Our atmosphere is transparent to visible light and some infrared, but fortunately, it is almost opaque to high frequency ultraviolet waves. The small amount of ultraviolet that does get through is responsible for sunburns. If it all got through, we wouldn't dare go out in the sun without protection. Why is wetter darker? Note the color of a surface and then wet it. How did wetting the surface change its appearance? Think. What happens with each bounce as light bounces around inside the transparent, wet region? Clouds are semi-transparent to ultraviolet, which is why you can get a sunburn on a cloudy day. Ultraviolet also reflects from sand and water, which is why you can sometimes get a sunburn while in the shade of a beach umbrella. Concept check. Why does light not pass through opaque materials? 27.6 Shadows. A thin beam of light is often called a ray. Any beam of light, no matter how wide, can be thought of as made of bundles of rays. When light shines on an object, some of the rays may be stopped while others pass on in a straight line path. Look at figure 27.9. A shadow is formed where light rays cannot reach. Sharp shadows are produced by a small light source nearby or by a larger source farther away. However, most shadows are somewhat blurry. Figure 27.9. A large light source produces a softer shadow than a smaller source. There is usually a dark spot on the inside and a lighter part around the edges. The total shadow is called the umbra. A partial shadow is called a penumbra. A penumbra appears where some of the light is blocked, but where other light fills in. This can happen where light from one source is blocked and light from another source fills in, as in figure 27.10. Or a penumbra occurs where light from a broad source is only partially blocked. A dramatic example of a penumbra occurs when the moon passes between the Earth and the sun during a solar eclipse. Look at figure 27.11. Because of the large size of the sun, the rays taper to provide an umbra and a surrounding penumbra. The moon's shadow barely reaches Earth. Why are lunar eclipses more commonly seen than solar eclipses? There are usually 2 of each every year. However, the shadow of the moon on Earth is very small compared with the shadow of the Earth on the moon. Only a relatively few people are in the shadow of the moon, solar eclipse, while everybody who views the nighttime sky can see the shadow of the Earth on the moon, a lunar eclipse. 27.10. The sharpness of a shadow depends on the distance between the object and the wall. A. An object held close to the wall casts a sharp shadow. B. An object is moved farther away. Penumbras are formed and cut down on the umbra. C. When it is very far away, all the penumbras mix together into a big blur. Figure 27.11. An eclipse of the sun occurs when the moon's shadow falls on Earth. If you stand in the umbra part of a shadow, you experience brief darkness during the day. If you stand in the penumbra, you experience a partial eclipse. The sunlight is dimmed and the sun appears as a crescent. Now look at figure 27.12. Earth, like most objects in sunlight, casts a shadow. This shadow extends into space, and sometimes the moon passes into it. When this happens, we have a lunar eclipse. Whereas a solar eclipse can be observed only in a small region of Earth at a given time, a lunar eclipse can be seen by all observers on the nighttime half of Earth. Shadows also occur when light is bent in passing through a transparent material such as water. In figure 2713, shadows are cast by turbulent rising warm water. Light travels at slightly different speeds in warm and in cold water. Figure 2712. An eclipse of the moon occurs when Earth's shadow falls on the moon. Figure 2713. A heater at the tip of this submerged J-tube produces convection currents in the water. They are revealed by shadows cast by light that is deflected differently by the water of different temperatures. The change in speed causes light to bend, just as layers of warm and cool air in the night sky bend starlight and cause the twinkling of stars. Some of the light gets deflected a bit and leaves darker places on the wall. The shapes of the shadows depend on how the light is bent. You will learn more about the bending of light in Chapter 29. Concept check. What causes the formation of shadows? 27.7 Polarization. Light travels in waves. The fact that the waves are transverse and not longitudinal is demonstrated by the phenomena of polarization. If you shake the end of a horizontal rope, as in figure 2714, a transverse wave travels along the rope. The vibrations are back and forth in one direction, and the wave is said to be polarized. If the rope is shaken up and down, a vertically polarized wave is produced. That is, the waves traveling along the rope are confined to a vertical plane. If the rope is shaken from side to side, a horizontally polarized wave is produced. A single vibrating electron emits an electromagnetic wave that is polarized. Figure 1114. A vertically polarized wave is on the left and a horizontally polarized wave is on the right. A vertically vibrating electron emits light that is vertically polarized, while a horizontally vibrating electron emits light that is horizontally polarized, as shown in figure 2715. A common light source, such as an incandescent or fluorescent lamp, a candle flame, or the sun, emits light that is not polarized. This is because the vibrating electrons that produce the light vibrate in random directions. When light from these sources shines on a polarizing filter, such as that from which Polaroid sunglasses are made, the light that is transmitted is polarized. The filter is said to have a polarization axis that is in the direction of the vibrations of the polarized light wave. Light will pass through a pair of polarizing filters when their polarization axes are aligned, but not when they are crossed at right angles. 2715. Polarized light lies along the same plane as that of the vibrations of the electrons that emit it. This behavior is very much like the filtering of a vibrating rope that passes through a pair of picket fences, as shown in figure 2716. When you skip flat stones across the surface of a pond, stones with flat sides parallel to the water bounce, reflect, but stones with flat sides at right angles to the surface penetrate the water, refract. Light behaves similarly. The flat side of a stone is like the plane of vibration of polarized light. Light that reflects at glancing angles from non-metallic surfaces such as glass, water, or roads vibrate mainly in the plane of the reflected surface. So glare from a horizontal surface is horizontally polarized. 2716, a rope analogy illustrates the effect of crossed sheets of polarizing material. The axis of Polaroid sunglasses are vertical, so that glare from horizontal surfaces are eliminated. Figure 2717 demonstrates the effect the orientation of polarizing filters has on the transmission of light. Concept check. Why is glare from a horizontal surface horizontally polarized? Figure 2717, A. Light is transmitted when the axes of the polarizing filters are aligned. B. Light is absorbed when they are at right angles to each other. And C. Surprisingly, when a third filter is sandwiched between the two crossed ones, light is transmitted. Discover, which eye do you use more? Hold a finger at arm's length with both eyes open. Look past your finger to a distant object. Now, close your right eye. Does your finger jump to the right? If so, then you use your right eye more. Check this by repeating with your left eye. Check with your friends. Is a left-handed person more likely to be left-eyed? Think, is a right-handed person more likely to be right-eyed? 27.8, polarized light and 3D viewing. Vision in 3 dimensions depends on the fact that both eyes give impressions simultaneously, or nearly so, each eye viewing a scene from a slightly different angle. To convince yourself of this, hold an upright finger at arm's length and see how it switches position relative to the background as you alternately close your eye. The view seen by each eye is different. The combination of views in the eye-brain system gives depth. Look at figure 2718. Figure 2718. When your left eye looks at the left view of the statement, while your right eye looks at the right view, your eye-brain system combines them to produce depth. The second and fourth lines appear farther away. To see this, place your face to the book with your nose touching the page. Now, very slowly, without trying to focus your eyes at any one point, move away from the figure. If you've moved 30 centimeters and still haven't seen the stereo effect, start over. It may take a few tries. A pair of photographs or movie frames taken a short distance apart, about an average eye spacing, can be seen in 3D when the left eye sees only the left view and the right eye sees only the right view. Slideshows or movies accomplish this by projecting the pair of views through polarizing filters onto the screen. Their polarization axes are at right angles to each other, as shown in figure 2719. The overlapping pictures look blurry to the naked eye. To see in 3D, the viewer wears polarizing eyeglasses with the lens axis also at right angles. In this way, each eye sees a separate picture, just as in real life. The brain interprets the two pictures as a single picture with a feeling of depth. 2719, a 3D slideshow using polarizing filters. The left eye sees only polarized light from the left projector. The right eye sees only polarized light from the right projector. Both views merge in the brain to produce an image with depth. Think, which pair of glasses is best suited for automobile drivers? The polarization axes are shown by the straight lines. Pair A is best suited because the vertical axis blocks horizontal polarized light that composes much of the glare from horizontal surfaces. Pair C is suited for viewing 3D movies. Handheld stereo viewers produce the same effect. Depth is also seen in computer-generated stereograms, as in figure 2720. Here, the slightly different patterns are hidden from a casual view. You can view the message of the figure, what this book is about, with the procedure for viewing figure 2718. Once you've mastered the viewing technique, head for the local mall and check the variety of stereograms in posters and books. Concept check. How can you see photographs or movies in 3D? Figure 2720. Read the message in this computer-generated stereogram. Figure 2721. Try each of the optical illusions below. Take your time and consider each very carefully before moving on to the next. Light. Light has a dual nature, part particle, part wave. Michelson's experimental value for the speed of light was 299,920 kilometers per second, usually rounded to 300,000 kilometers per second. The electromagnetic spectrum consists of radio waves, microwaves, infrared, visible light, ultraviolet rays, X-rays, and gamma rays. Light passes through materials whose atoms absorb the energy and immediately re-emit it as light. In opaque materials, any coordinated vibrations given by light to the atoms and molecules are turned into internal energy. When light shines on an object, some of the rays may be stopped, while others pass on in a straight line path. Light that reflects at glancing angles from non-metallic surfaces vibrates mainly in the plane of the reflecting surface. A pair of images can be seen in 3D when the left eye sees only the left view and the right eye sees only the right view.